Hello everyone, this is an e-lesson on the Ford-Fulkerson algorithm for max flow. Why is max flow important? Max flows are important since they show the maximum rate and corresponding path for getting an entity from one place to another through some infrastructure. The most obvious application is waterworks, sewage and drainage. Now we will look at the Ford-Fulkerson algorithm itself. Overall, the Ford-Fulkerson algorithm behaves as follows. First, create a flow graph from the input capacity graph with all the flows set to 0 and create a corresponding residual graph. Then, while there exists a non-zero path in the residual graph from the source to the destination, add the weight of the minimum weighted arc in this path to the flow graph and update the residual graph appropriately. Once there are no more non-zero paths from the source to the destination, the algorithm returns the flow graph.
Knowing the algorithm, we can now work through two examples, one showing how this would be used on a typical graph, and another to illustrate the potential inefficiencies of the algorithm. First thing we must do is to find a path from the source node S to the destination node T along arcs of capacity greater than 0. For example, we could move from S to node 3 along an arc of capacity 5, and then from node 3 to T along an arc of capacity 7. Next, we must find the minimum arc capacity along the path we have found from S to T. On this path, we have an arc of capacity 5 and an arc of capacity 7. The minimum of these is 5. What we must do then is to push 5 in flow from S along the path to T. To do this, we must first erase the values of each arc, and then we must replace these values by new values according to what we have pushed. On the forwards arcs, we need to replace the value by the original value minus what we have pushed. For example, here, the original value was 5, we have pushed 5, and so we've got a new value of 0. Similarly, over here, we originally had 7, we've pushed 5, and so we've got a new value of 2. On the back edges, we need to add what we have pushed to our original value. On both of these back edges, our original value was 0, and so our new value will be 0 plus 5, number we have pushed, which gives us 5. The last thing we need to do is to update our original capacity graph with the new flow we have going through it. To do this, all we need to do, since this is the first stage, is to add the number onto our capacity graph on the forward edges on our path. And now this value corresponds with our residual graph. For our second iteration, we need to apply the same process on the residual graph, finding a path from S to T along arcs with weight not equal to 0. On our first iteration, we set this arc here to have a weight of 0. Hence, we cannot follow this arc to get from S to T. Instead, we'll follow this path here on our way from S to T. On the path we are following from S to T, we need to find our minimum arc weight. We've got 16, 17, 14, and 20. The minimum of these is 14. Hence, we need to replace each of these numbers on our forward arcs with their current value minus 14, and the corresponding backwards arcs with their current value plus 14. To do this, we need to erase the values from their arcs on the path we are following, and then replace them by their updated values. For this arc, the original value was 16 on the forward arc. we are pushing 14, and hence the new value is 16 minus 14, which is 2. The backwards arc, the original value was 0, we are pushing 14, and so our new value will be 0 plus 14, which is 14. This arc, the forwards arc, had an original value of 17, giving a new value of 3. And the backwards arc had an original value of 0, giving a new value of 14. Over here, our original value was 14 on the forwards arc, giving a new value of 0, and on the backwards arc, we had an original value of 0, giving a new value of 14. On the final forwards arc, we had an original value of 20, giving a new value of 6, and an original back arc of 0, giving a new value of 14. Finally, we need to update our capacity graph with the new flow we have pushed through it. Since none of the arcs on our path already have any flow flowing through them, we can simply append the pushed flow onto the front. We will then continue to apply the iterative process until there are no more paths from S to T on our residual graph where all the arcs are greater than 0. If we find that we need to push through an arc we've already pushed through, for example, we might find another path which pushes from S through 2 and then somewhere else to T, we simply add the push value onto our current flow. If we find we need to push along one of the back edges in our residual graphs, for example, we might need to push from 4 through to 2, then we simply subtract the value that we are pushing from the current flow in this arc. Once the iterative process is complete, your capacity graph will look like so, and your residual graph will look like so. Next, I will show by demonstration the problems with the Ford-Fulkerson algorithm. To demonstrate this, I will be using this graph here. As can be seen from a simple cut, this graph has a maximum flow of 2000. However, the Ford-Fulkerson algorithm will choose a random path from our source node S to our destination node T. For example, it might go from S to node 1 to node 2 to node T. The minimum value here is 1, and so we need to update our path with the value of 1. After updating the two graphs, they will look like so. On the second iteration, the Ford-Fulkerson algorithm may decide to go from S to node 2 to node 1 to T. As you can see, the minimum capacity on this path is 1. Hence, we will need to update for a flow of 1. After updating the two graphs, they will look like so. As you can see, this process could go on for a very long time, alternating between these two paths. Since we know that the max flow is 20,000, and we can update a minimum of 1 for every single iteration, we know this may take up to 20,000 steps in order to find the maximum flow in the graph. As for the algorithmical complexity of the Ford-Fulkerson algorithm, it is rather easy to analyse. As we have seen, the maximum number of iterations that can be performed by the Ford-Fulkerson algorithm is the maximum flow through the graph, since each iteration must increase the flow by at least 1. Each iteration takes, at the most, each edge into account once, meaning the running time for a single iteration is order of the number of edges. If we denote the maximum flow as f star, then the maximum runtime of the algorithm is order of e times f star.